Hello, welcome to another class from the course Understanding Electricity and Electronic Devices by Q in Motion. Today, we're going to talk about voltage regulation and Zener diodes. As usual, before we go on, let's talk a little bit of some concepts that we studied in previous classes. So we talked about rectification, which is a conversion from AC to DC. We saw that diodes and capacitors are used for this. We studied the half-wave rectifier, which is very basic and has pretty poor performance. And we also studied the full-wave rectifier, and we saw how that is much, much better and much more efficient. We also saw that DC quality could be improved by filtering with capacitors, but still the output is far from perfect. We saw that it had a lot of ripple. Those are those little waves that were riding on top of the DC rectified voltage. And finally, we also saw that peak voltage is not the same as RMS voltage in AC. And this is very important when we use rectifiers because the DC voltage of the rectifier is going to be closer to the peak voltage and not to the RMS voltage of the original AC voltage. So let's talk about voltage regulation, which is the main topic of this class. First of all, what is a voltage regulator? That would be a circuit or a device that maintains constant output voltage under varying input voltages and load conditions. For instance, here we have an input voltage that varies between 6 and 12 volts and an output current varying between 0 and 2 amps. And the voltage regulator's function is to ensure that under these conditions, the output voltage is steady at 5 volts. One of the main applications of a voltage regulator is to obtain better DC after rectifying and filtering. Here we have the full wave rectifier and filter that we studied last class, powered with a 9-volt AC voltage. Here we have the same traces we studied last class, with voltage varying, an AC voltage varying from 0 to a peak of about 12.5, and then going down to negative 12.5 and repeating every cycle. After the full wave rectifier, we flip the negative cycles or the negative half cycles of the AC and make them positive, right? So the output of the rectifier is this orange trace that goes up and back to 0, up and back to 0, and so on. The next thing we did was to filter that full wave rectified signal or voltage, and then we obtained the one in red, right? So the capacitor gets charged to the peak voltage and then slowly discharges until the next half cycle charges it again, and so on. So we would have this waveform here. Now, while this is closer to a DC, it has these variations between about 12 volts and down to 10 volts and up again. If we add a voltage regulator after this filter with the capacitor, the voltage regulator is going to ensure, and assuming this is a 6-volt regulator, as long as the input voltage to the regulator, which would be the red trace, is within certain limits, the output is going to be very, very steady at 6 volts. So this is the first or the major application of using a voltage regulator. It would be to obtain a pretty much perfect DC voltage after rectifying and filtering AC. So what are other applications of voltage regulation, right? So that we just saw one, which is after rectification to obtain an almost perfect DC. Another one would be batteries discharging, right? So if we have, say, 4 alkaline batteries providing a total of 6 volts, that's 6 volts when the batteries are new, but as they discharge, you will see the voltage lowering to 5 or 4.5, for instance. So we could use a voltage regulator to maintain a constant voltage as the battery is discharged. Another application would be to lower voltage from 5 volts, which could be provided by a USB port, and lower that to, say, 3.3 volts, which is a pretty typical voltage that many digital circuits use nowadays. Another application would be universal power supplies, for instance, for traveling. So something that you can plug into a 120 volt outlet in North America, or 220 volt outlet in Europe. And in spite of being double the input voltage, you will still be getting the same voltage that you need for your device. Most modern power supplies contain a voltage regulator nowadays. So that brings us to the topic of Zener diodes, which are a special kind of diode. When we studied regular rectifying diodes, we studied that they can block only so much voltage when connected in reverse. And that was one of the main parameters that you would have to specify when you specify if you want to purchase a rectifier diode. One of the main parameters would be how much voltage they can block when in reverse. Zener diodes are actually used in reverse bias to the point where they cannot block anymore. So you would specify those to a voltage that is within the voltage of the circuit you're using. And they come in different voltages, for instance, 3.3 volts, 5.1, 12 volts, etc. Okay, so let's see how we can use one of these Zener diodes. A Zener diode can be combined with a resistor to create a voltage limiter, and this would be the circuit, for instance. So we have an input voltage which varies, and then a resistor, and then our Zener diode. And then we have an output voltage which is measured or taken between the anode and cathode of the Zener diode. By the way, this is the symbol of the Zener diode, and in the previous slide, we saw what they looked like. They look like these glass diodes with the cathode marked with a band on a different color. So what happens with this circuit when we vary the voltage from 0 to, say, to 10 volts? At the very beginning, the voltage is, as you can see, it's in reverse bias, right? So it's positive on the cathode and negative on the anode. So the diode does not conduct. So current through the resistor is 0, so 0 drop, and the voltage here in parallel with the diode is going to be the same as the input voltage. So the voltage, the output voltage is going to be increasing following the input voltage to a point where the diode cannot block anymore. And this is a 3.3 Zener diode, and it's going to start conducting a little bit, usually a little bit below the 3.3 volts. In this case, we have 3.2 volts. At this point, it's going to be increasing very little, maybe from 3.2 here to 3.3 in the middle and 3.4 over here. So you see where this is going, right? We have a voltage, an input voltage that varies between 3.3 and 9, and which is a very large variation, right? 6 volts on the input. And the output voltage varies from maybe 3.2 to 3.4. So that's almost nothing, right? Very little. So this circuit is limiting the input voltage, right? Because the input voltage doesn't go above 3.4. The output voltage doesn't go above 3.4 when the input goes up to 9. But it is regulating actually, right? You see where this is going. This is acting as a regulator because within this range, the output voltage is held almost constant with a very wide varying input voltage. Okay, so now that we know what we want to achieve here, let's try to calculate the resistor on a regulator. So the minimum value of the resistor is going to be limited by the maximum power that the Zener voltage can dissipate. And for small diodes, this is typically around 1 watt, okay? So if we want to calculate the power dissipated on the Zener diode, that's going to be equal to the current through the Zener diode times the voltage, right? And the voltage, it's defined by the characteristic of the diode itself, in this case, 6 volts. Now the current, it's going to be the input voltage minus the Zener voltage divided by the resistor, okay? That's simply applying Ohm's law to this resistor. And substituting this current into the power equation, we end up that the maximum input voltage minus the Zener voltage over the resistor times the Zener voltage has to be lower than the maximum power allowed to be dissipated on the Zener diode. Okay, so let's calculate an example. This is just a copy of the last equation. And let's calculate the minimum value for a resistor in Zener diode regulator, where the Zener is specified at 6 volts, 1 watt, and it is fed by the output of a rectifier whose output varies from 9 volts to 12 volts. So substituting taking this equation and solving for the resistor, we end up with this equation here. And substituting those values, right? 12 volts is the maximum input voltage, right? Minus 6 volts, which is the Zener voltage, divided by 1 watt, which is the maximum power that the diode can handle, times 6 volts, which is the Zener voltage again. That's the minimum resistance, and that ends up being 36 ohms, okay? So the maximum value of the resistor is going to set by the maximum current and the lowest input voltage. And we have to ensure that the voltage here still remains at 6 volts or whatever voltage we want here for the Zener. So what happens here when we connect these to a load and the load starts taking current, we're going to be increasing the voltage drop on this resistor, right? Remember from Ohm's law, the voltage drop is the current times the resistance. So if we increase the resistance, the voltage here is going to start to drop, okay? So if we have a minimum voltage here and we take too much current here, let's say we have 10 volts, we have 10 ohms here, and we take half an amp here. So half an amp times 10 ohms, that is 5 volts dropping. So we had 10 volts here, 5 volts dropping here. We end up with 5 volts here, which is less than the Zener voltage, and we wanted to maintain at least 6 volts here, right? So the Zener turns off, does not conduct anymore, and we end up with less than the Zener voltage on the output. So mathematically, this is the equation: the minimum input voltage minus what we're losing on the resistor has to be more than the Zener voltage. And solving for the resistor, we end up with this equation: the minimum input voltage minus the Zener voltage divided by the maximum current. So how can we use this previous equation to calculate the maximum value for a resistor in a 6 volt, 1 watt Zener diode regulator fed by the output from a rectifier whose output varies from 9 volt to 12 volt? So it's the same example we had before with the 6 volt, 1 watt Zener diode and regulator output varying from 9 to 12 volts, okay? The maximum expected current is 50 milliamps, and then we're going to repeat that for 80 milliamps. So this is the equation we had on the previous slide, and replacing the values with a 50 milliamp maximum current, we end up with a maximum resistor of 60 ohms. Now, if we were to connect this to a load that takes 80 milliamps and we repeat the calculations, we will end up with a maximum value of 37.5 ohms here, okay? So the higher the output current, the lower the resistor has to be. So let's put all these values together. In the previous example, we calculated that the minimum value of the resistor is 36 ohms, and the maximum value is 60 ohms if we want a maximum current of 50 milliamps, or a maximum value of 37.5 for 80 milliamps current to the load. So this means for a regulator that can deliver 0 to 80 milliamps, the resistor has to be between 36 and 37.5 ohms, okay? So this is very limiting. As you can see, pretty much we have no margin for error on the resistor, okay? And we are only delivering current in a range from 0 to 80 milliamps. 80 milliamps is not a lot of current, really. So this circuit that we saw here as a voltage regulator performs pretty poorly, okay? How do we make a better voltage regulator? Well, we can improve it by adding a transistor to this circuit, right? A transistor connected like this. We have not studied transistors yet, but when we're going to get back to this circuit when we study transistors. And the way this works is transistors have a parameter called beta that is the current gain of the transistor. So basically what it does is when you have a load here that varies the current, the transistor is going to be supplying the current through this path. This is called the collector and this is the emitter, right? So the resistor will be supplying the current through this path, and the current supplied through this path, which is the base, this terminal is called the base of the transistor, the current is going to be much, much lower. So in the case of the previous examples, we may have a current varying between 0 and 50 milliamps here, which is what this regulator is going to be providing. And this may be translating in a current varying from 0 to 1 amp over here, okay? So this is how the transistor can improve it. We keep the resistor and the Zener diode within a limited operating zone, which is maybe 0 to 50 milliamps, and we can deliver 0 to 1 amp to the load. We're going to get back to this circuit when we study transistors, like I said, but next class, we're going to see devices that perform much, much better than even this regulator, okay? So if Zener diodes are not very good for regulators, unless you combine that with something else, and like I said, there are even better solutions for voltage regulation. Why are we studying Zener diodes? Okay, so Zener diodes could be useful by themselves as voltage limiters, right? For instance, we have some kind of digital circuit that accepts signals as 0 and 5 volts. So digital circuits work in binary. So 0 is represents internally like a 0 in a binary notation, and 5 volts represents a 1, right? But the problem is that this circuit, if you put more than 5 volts into this circuit, you may be damaging it. So let's assume we want to interface this with another circuit that is not known yet, right? Because we want to provide an interface to a wide variety of circuits, right? And this circuit provides, for instance, 5 volts, 12 volts, or maybe even 25 volts as a representation of a binary 1. When we put this circuit here, the voltage, when this is 0 volt, it's going to be 0 because the Zener is not conducting and not turning on. And instead, when we have 0, 12, or 24 volts, this Zener diode is going to start conducting, and it's going to be limiting the voltage to 4.7 or 4.8 volts, okay? That's very close to the 5 volts that this circuit is going to be recognizing as 1, and it's going to be below 5 volts, and that is going to be protecting this circuit. So that's one of the applications where you may want to use a Zener diode, okay, to protect this circuit from an overvoltage. Okay, so let's do a quick review of what we saw today. We studied Zener diodes. They are used in reverse to the point where they cannot block the voltage anymore. And they are available in different voltages, right? So you purchase those, or you specify the Zener diode to the voltage that you want to have. They act as voltage limiters, as we saw in the previous slide, and they have fairly poor performance as voltage regulators by themselves. So they would have to be combined with transistors and maybe some other devices to perform well as voltage regulators. And like I said, they are useful to protect devices from overvoltage. Okay, so that is all for today. I hope you learned about voltage regulation and Zener diodes, and we'll see you next class with where we're going to study some better options for voltage regulation. Thank you, and see you next time.